everyone. Welcome to the second session on synthesis. I'm Cristina David. I'm from University of Bristol, and I'm going to chair this session. We have 5 very interesting works, so I think it's going to be great. Please do remember to ask questions on Slack. So as you already know by now, I'm sure there is a thread associated with each paper. So just post your questions there. Another announcement, at the end of this session, please join the breakout room. Okay, and let's start with the first speaker, who is Shaul Almagor from Technion Israel, and he's going to talk to us about good enough synthesis.
Hi there, I'm Shaul Almagor, and I'd like to tell you about good enough synthesis. This is a joint work with Orna Cooperman. Let's start by recalling the traditional LTL synthesis paradigm. There, we are given as inputs an LTL formula phi over 2 sets of atomic propositions, I, inputs controlled by the environment, and O, outputs controlled by a system. We then use a synthesis machine, yours may not look exactly like this one, which outputs a transducer that realizes the formula, if one exists. This transducer is a system which interacts with an environment and guarantees that every interaction results in a computation that satisfies phi. Let's see an example of synthesis. Consider the formula always a request implies that eventually there is a grant, where requests are inputs and grants are outputs. That is, every request from the environment should be eventually followed by a grant from the system. Can this formula be realized? Certainly. Here is a transducer that realizes it. Whenever it sees a request, it immediately issues a grant. And if a request is not given, it does not issue a grant. Now let's try another example. This time we want that infinitely often we see both a request and immediately a grant, and infinitely often we see no request and no grant. Well, this formula is not realizable, and the reason it's not realizable is that the system cannot force the environment to output infinitely many requests and infinitely many non-requests. Well, that's not really fair, is it? Alright, well, how about if the environment gives a hopeful computation, one that does have infinitely many requests and non-requests? Well, in this case, the same transducer above works just fine. So while this formula is not realizable, I would say it is good enough. Okay, some formal definitions. We work with formulas over input signals I and output signals O. And we model systems by strategies, which are usually given by transducers. A strategy takes a sequence of input signals, each of which is a subset of I, and outputs an output signal, which is a subset of O. Then, given an infinite input sequence such as X here, the strategy generates an infinite sequence of outputs, and this induces the infinite computation here. We then say that F realizes the formula if for every input X, the induced computation satisfies the formula. This is all completely standard. We're now ready for the new definitions. An input sequence X is hopeful if it can be matched with some output sequence such that the induced computation satisfies the formula. Note that crucially this does not mean that Y can be generated by a strategy. It just means that there is some match for X. We now say that a strategy F good enough realizes phi, or just GE realizes phi, if for every hopeful input sequence X, the induced computation satisfies the formula. And the fundamental problem we start with is GE synthesis. Given a formula, compute a transducer that GE realizes it, or report that there is no such transducer. Wow, look at all the colors. The notion of GE synthesis can be placed in the broader spectrum of limiting the environment in synthesis. Other approaches in this direction include adding direct assumptions on the environment, bounding the size and hence the computational power of the environment's implementation, or by adding a separate goal for the environment, making it more rational than hostile. GE synthesis is also closely related to works on dominant strategies. The strategies we look for may not be winning in the synthesis game, but they are good enough in the sense that they dominate all other strategies for the system. And there are several works on that. Results time. The first thing we show is that GE synthesis is 2x time complete. This is great news as it matches the complexity of traditional synthesis. 2x time hardness does not trivially follow from that of traditional synthesis, but the same reduction used to show hardness for synthesis in fact works for G synthesis as well. We won't go into that. A quick sketch of how we show membership in 2x time. We first employ the logic QLTL, which extends LTL with some quantification. We can use it to state the fact that X is hopeful by saying that X satisfies the formula exists outputs such that phi. Because indeed, X is hopeful exactly when there exist matching outputs such that the induced computation satisfies phi. This is what exists outputs such that phi means. We can now say that a transducer T GE realizes phi if and only if T realizes, in the traditional sense, the formula phi or for all outputs not phi. And this is because this formula says that for every input X, either the computation induced by T satisfies phi itself or X is not hopeful. So now all we need to do is solve synthesis for this formula. We do this via a sequence of automata constructions. We start with the LTL formula phi and use the Vardy-Wolpert translation to non-deterministic Büchi automata to obtain an automaton that is equivalent to phi and an automaton that is equivalent to the negation of phi. These constructions involve a single exponential blowup. We now take the automaton for phi and introduce more non-determinism by projecting away the outputs. This gives us a non-deterministic automaton equivalent to the formula exists output such that phi. Note that there is no blow up in size here, just possibly adding edges. We now take the product of this automaton with that of the negation of phi and end up with a non-deterministic automaton for the negation of phi and exists output such that phi. We now take this automaton and dualize it. Instead of a non-deterministic Büchi automaton, we get a universal co-Büchi automaton for the complement language, which is exactly the formula we were looking for. Observe that this involves no blow-up at all. Finally, synthesis for universal co-Büchi automata can be solved in x time, giving us a total of 2x time. A nice feature of this construction is that it doesn't go through deterministic automata, so we avoid a Safra construction, which means that our construction should relatively handle optimizations well. Alright, we solved the basic question. But wait, there is more. GE synthesis invites many types of extensions, some borrowed from similar ideas in traditional synthesis and some are new. We'll now look at a few of them. Adding strong guarantees, which essentially combines the traditional and the GE settings. Raising flags, which indicate the hopefulness status of inputs. Quantitative extensions, taking us beyond the Boolean setting, and the stochastic setting. We'll start with the strong guarantees setting, where in addition to the formula phi, which we now call phi weak, we are also given another formula, phi strong. The problem is then to find a transducer that realizes phi strong as well as GE realizes phi weak. You can think of phi strong as requirements that have to be met no matter what. For example, the machine should not explode, whereas phi weak should be satisfied if it's at all possible. For example, issue infinitely many grants for requests as long as infinitely many requests are given. We show that this problem is also 2x time complete. The proof is by appropriate modifications of the automata construction we showed earlier. The next extension we look at involves raising flags. The motivation is that as the system interacts with the environment, it typically doesn't know if the given input is going to be hopeful or not. But sometimes we can determine after a finite prefix if the input is going to be hopeful. Suppose we have some word over inputs and outputs, such that after seeing it, the language of remaining suffixes is realizable, in the traditional sense. We call such words green, or green flags. We lift this to input words by saying that an input word is green if there is some output that would make it green. The nice thing about green prefixes is that we can identify them using a monitor, which is just a deterministic finite automaton with outputs. So if we equip our transducer with such a monitor, it can raise a flag whenever a green prefix has been seen, and we can be assured that from now on the formula is realizable. And if our transducer is GE realizing, then we are also assured that the formula will be satisfied. We can think of green flags as giving information about satisfaction. There are some other flags we can consider. Red flags tell us that no matter what output was given, all the remaining suffixes are doomed not to satisfy the formula, so we can give up. Dually, blue flags tell us that there exists an output such that every remaining suffix satisfies the formula, so from now on there is no reason to actually look at the inputs as anything will work. We can construct monitors for these flags as well. The next extension we look at is the quantitative setting. This extension already exists for traditional LTL synthesis, where instead of asking whether a formula is satisfied, we ask how well it is satisfied. There are many quantitative extensions to LTL. Here we consider LTL-F, which extends LTL to a multi-value domain by allowing the designer to introduce arbitrary quantitative operators. I'll demonstrate this logic with an example. Suppose I'm riding in an autonomous car, and I realize this is completely unrealistic since we're no longer allowed to go outside, but we're aiming at future technologies. My car has an acceleration control, which normally should keep it in a relatively constant speed. However, if the car recognizes a long stretch of road that is obstacle-free, it should accelerate to optimize time travel. We formalize this requirement as always, if the road is safe, then accelerate for 2 consecutive steps, and this operator means weighted average. If we accelerate for 2 steps, the satisfaction value is 1. If we only accelerate in the first step, we get a satisfaction value of 2/3, and if we only accelerate on the second step, we still get 1/3 satisfaction. So this prioritizes the acceleration over the 2 steps. Now, if at some point the car recognizes an obstacle, then it should similarly decelerate for 2 consecutive steps, this time with a weighted average of 3/4, making it more important to slow down immediately. Finally, we're of course not allowed to accelerate and decelerate simultaneously. So can this formula be realized? Or more accurately, with what value can it be realized? Well, not with value 1. The reason is that a priori, there is nothing preventing obstacles and safe stretches to appear in alternating steps, in which case we cannot either accelerate or decelerate for 2 consecutive steps. But we still want to do the best possible, since in reality most roads do not have alternating moves. But we don't want to add this as an explicit assumption either. This is what GE synthesis does in the quantitative case. It guarantees the best possible results for each input. That is, for each road condition, the synthesized autonomous car has to obtain the maximal satisfaction value that is possible for that road condition. Note that this is not achievable with current definitions of synthesis and its extensions. To make this a bit more precise, the traditional synthesis problem for LTL-F is the following. Given a formula phi and a threshold v, compute a transducer that achieves value of at least v for every input computation, or answer that no such transducer exists. In 2016, we studied this quantitative extension, and in particular solved the synthesis problem for it. We show that the complexity is still 2x time. So how do we lift this to GE synthesis? It's actually not entirely clear, and we propose 2 approaches. In the first approach, we're again given a threshold v, and we want to compute a transducer that achieves value of at least v for every v-hopeful input sequence, where a sequence is v-hopeful if there is some output for which it gives value at least v. This makes sense, but it doesn't quite capture quantitativeness, since we essentially reduce the quantitative aspect back to a Boolean one using a threshold. A more quantitative approach takes only a formula and computes a transducer that gives, for every input x, the maximal possible satisfaction value that this input can give over any output. This is in a way the best transducer for the formula, which I guess means that best and good enough coincide, having huge implications on my child's ability to clean his room, but I digress. Complexity. The complexity of this problem is 2x time complete. Of course it is. Now let's look again at this problem. We see that in a way, the transducer here gives a different guarantee of satisfaction value depending on how hopeful the input is. This has an assumed guarantee flavor, which we want to extend a bit. Instead of considering the Boolean assumption is x v hopeful and responding with the Boolean guarantee satisfy with value at least v, we can combine the hopefulness and the satisfaction value in a quantitative manner. We do this using a function comb, which, as its name suggests, combines the satisfaction value of the hopefulness formula, exists output such that phi, with the satisfaction of the actual formula phi. The function is given by the designer and should satisfy a very small and reasonable set of monotonicity properties. We'll see examples in a second. Now, the GE assumed guarantee realization value of the formula phi by a transducer T is the minimal combined value over all inputs. And the corresponding synthesis problem is to find a transducer that maximizes the realization value. And guess what? This can be solved in 2x time. Some natural examples of the function comb are a quantitative version of implication, taking the maximum between the negation of the assumptions and the guarantees. This means that a high value is attained if either the guarantees are high or the assumptions are low. Another example is 1 minus the difference between the assumptions and guarantees, which measures how close the guarantee is to the assumption. In our case, how close we are to matching the hopefulness. And finally, we can measure the relative success using the ratio of the guarantee and the assumptions. Each combination function suits different settings. We elaborate on this in the paper. The last extension we look at is the stochastic setting. Instead of looking at adversarial environments, we have a stochastic environment generating inputs randomly, and we want to maximize the expected satisfaction value. Oh, and we're actually going to start with a quantitative specification in LTLF, because why not? In 2016, we showed that we can solve this problem for LTLF in, say it with me,
2x time.
2x time. Extending the stochastic setting to the good enough setting is again not clear-cut, and we propose two approaches. In the first approach, we again use the combination function, and we measure the expected value of the combination. Then we try to find a transducer that maximizes this expected value. Intuitively, this means we take into account all inputs and factor in the hopefulness within the satisfaction value using the combination function. In the second approach, we still take the assume guarantee perspective, but we use a stochastic version of assumption by means of conditional expectation. So we look for a transducer that maximizes the expected satisfaction value of the formula, conditioned only on inputs that are v-hopeful for some v. In contrast to the first approach, here we actually factor out all the non-hopeful computations. Both of these versions are, of course, 2x time complete. Okay, let's summarize. Good enough synthesis is a relaxation of traditional synthesis which focuses on hopeful inputs. It is open to many variants. Strong guarantees, where we combine GE synthesis with traditional constraints. We can add flags that indicate the hopefulness status of prefixes. The setting has several extensions to the quantitative domain, which are particularly useful for autonomous systems, as well as to the stochastic setting. Moreover, these extensions can be combined, as the jars here suggest. For example, we can add flags to the quantitative setting. The complexity of the problems when solved carefully is 2x time, matching that of LTL. And finally, we have the benefit of several serverless algorithms. Thanks for listening.
Hi. Managed to unmute my mic. Thank you very much for the talk. It was very nice. I really think it's a very interesting relaxation of the traditional LTL synthesis problem. And I do have some questions. You discuss a few synthesis problem. So you have obviously the G synthesis problem, and then you have all these extensions, and I assume you are going to have different automata constructions for each of them. So my question is, do you have any insight into whether some of these problems are more tractable than others?
Yeah. So the quantitative setting does go through deterministic automata. We don't have a construction that avoids Suffolk construction for LTLF. So the quantitative stuff may pose a challenge, but it still might be tractable using some clever constructions. For example, if the set of functions used in LTLF is not very elaborate, we might be able to somehow circumvent Suffolk's construction. We actually haven't looked a lot into sufferless constructions for LTLF, so it's possible that there are some constructions. But overall, as you saw in the proof, the automata constructions we use are very standard, so they're likely to be quite tractable as LTL is. However, if you look at fragments such as GR1 synthesis, then it doesn't keep, it's not trivial that it maintains the good complexity of GR1, because this quantification over the outputs can ruin things, basically. So for really efficient LTL stuff, we don't know. That's a good open question to study.
Okay. Also, when you showed the automata construction, when you're proving membership to Epstein, I was wondering, like, probably you may be able to use quite a few of existing tools, right? There. So how do you envision kind of having?
When you say tools, you mean actual tools, right? Not.
Yes, yeah. So are there, I assume that for some of those constructions.
Honestly, I have no. I mean, the honest answer is that I have no idea. But the constructions themselves are not elaborate. So the projection operator over the outputs is pretty standard. I would guess it's very easy to implement in any tool, but I don't know too much about tools to actually give a decent answer on that.
Okay. Let me see if there is anything.
There are a couple. There is one question on Slack by Loris.
Yeah.
So we asked, I missed a bit of the talk, so maybe it said this, but is the relationship between this formulation and the work on repair without regret from Jobsman? I don't know. So Loris, if you can elaborate on that, because I recall this work very vaguely, but I'm not sure. I remember the details enough to comment on that. Maybe he's not here.
There is another question until then from Shibashis. Sorry, I'm gonna mispronounce a lot of names. So thanks for the nice talk. Have you considered the case if the specification is given in terms of an automaton like GFG?
No, we haven't looked at GFG automata. So I guess the question is that for GFG automata, synthesis may be easier because we don't have to determinize. My guess is that as long as projection maintains GFG, we should be fine. If the projection on the output ruins something, then we can't use that. I'm not sure that I'm fairly certain that projection can ruin GFG, but we haven't looked at the details. But it's also a good question. So this is, there are a lot of extensions we haven't looked at.
Okay, great. Well, thank you very much. I think the time is up, and we can move on to the next talk, which will be given by Martin Kobel from University of Constance, and it is about TarTar, a timed automata repair tool.
Welcome everybody, my name is Martin Kobel. I'm a PhD student at the University of Constance, and today I'm talking about TarTar, a timed automata repair tool. This joint work with Stefan Loye and Thomas Wies. As a running example, we will use this network of a timed automata. The model has locations and transitions between the locations. Also, the model contains clock variables, for example x, which we can reset to 0, or increase the values inside of a location. The possible evaluations of a clock are restricted by the time constraints. For example, invariants that always have to hold inside of a location, or transition guards which have to be enabled to take a transition. This model contains a client which sends a request to a database. The property that we want to ensure for this model is that between sending and receiving of a request are at most 4 time units. Therefore, we reset the clock x with sending the request and check it again in the receiving location. A real-time model checker such as UPAL will detect following execution. First, the client creates the request and sends the request in 1 to 2 time units to the database. The database processes the request in 1 time unit and the response in 1 to 2 time units. Overall, the request can take up to 5 time units, which is above the 4 time units of requirement. UPAL returns this counterexample as a time diagnostic trace, or TDT for short. TarTar analyzes this TDT to compute syntactic repairs. One repair is, for instance, to exchange the invariant allocation so receiving with set small equal 1. This reduces the time for receiving the response to 1 time unit and removes the property violation. Also, TarTar ensures that the computed repairs are admissible, which means that the original and repaired NTA are functional equivalent. The rest of the talk I have structured as following. In the first part I will explain how TarTar computes repairs, I give insight to the logical encoding of the TDT, the computation of the repairs and the admissibility check. In the second part we do a tool evaluation. Let's start with logical encoding of the TDT. The TDT of the database is a transition sequence theta 0 to theta 3. We encode the time constraints of these transitions in linear real arithmetic and result with a logical constraint system that allows only clock assignments that are possible in the timed automaton. We exemplify our encoding by the invariant set smaller equal 2 and the 4th location so receiving. For the encoding we create a variable set4 that has the value of set with entering the 4th location, and a variable delta4 which describes the delay in this location. The invariant set smaller equal 2 is satisfied as long as the sum of set4 plus delta4 is below or equal to value 2. and this way we encode also the other time constraints of the TDT, the guards, reset, and delays, and result with a constraint system tau. Next, we add potential repairs to tau. Therefore, we insert variation variables v in the time constraints. For instance, we can modify the invariant set small equal 2 by adding a variable v to its bound, and use an SMT solver to find the assignment -1, which repairs the NTA. In the same way, TarTar also computes other syntactic repairs. For instance, a repair can exchange the clock z of the invariant with clock y, and result in the invariant y small equal 2. Or a repair can make the location so receiving urgent, which means that the location has to be left immediately without a time delay. Another syntactic repair is to exchange the operator in a time constraint. For instance, w greater equal 1 becomes w smaller 1. Or to change the set of clocks. Overall, TarTar can find 5 kinds of syntactic repairs. After computing a set of repairs, we want to ensure the admissibility. A repair changes the time traces that are possible in a model. On the one hand, we want to remove time traces from a model that reach a property violation. On the other hand, we don't want to remove functional behavior. For instance, the repaired invariant set smaller equal 1 in the location so receiving disables the transition towards the timeout location. So this repair is not admissible since the location is no longer reachable. The functional behavior of a model is the sequence of transitions that can be taken. To compute the possible transition sequences, we remove the timestamps from the time traces and result with the untimed language of the model. For the admissibility check, TarTar compares the untimed language of the original repaired model. Now we know how to compute repairs and how to check their admissibility. On this slide you can see the architecture of TarTar. Next we want to evaluate TarTar. For an evaluation we need NTAs that violate the properties, but a benchmark with broken timed automata does not exist. Thus we have taken 8 correct models from the literature and seeded faults in them of the same kind as our repairs. Next we check whether UPAL finds TDTs for the corrupted models. This creates 175 TDTs. For these 175 TDTs, TarTar now computes all kinds of repairs and uses therefore the SMT solver set 3. And checks for every repair whether it is admissible with a time model checker OPAL and a library automata lib. Overall, we found 1169 admissible repairs. And at least one admissible repair for 122 of the TDTs. This means that we repaired 69% of the TDTs. To conclude, we have seen TarTar, a repair tool that can compute 5 kinds of syntactic repairs and check their admissibility to ensure functional equivalence. The experimental evaluation shows that TarTar can compute an admissible repair for 69% of the TDTs. Also, the result shows that every repair analysis on its own is less efficient. Thanks for your attention.
Thank you very much. Sorry. Okay. Thank you very much for the talk. It's definitely a useful tool that I'm gonna keep in mind. So I have some questions. Did you consider ranking the repairs? So I understand that, you know, for each TDT you might get several repairs, right? Is there any way in which you would rank them?
No,
I mean,
the only obvious ranking is that the number of modifications that happens in the system, the less they are, the better. But we don't know any possibility to rank if it's better to in another way. So it's on the purpose what you want to do with the system and the property violation, which one is the correct one.
Okay. Okay, that's fair. Also, so I might have missed this, but did you mention anything about the timing? You know, like kind of how long would it take on average or for a repair to be found? I don't. Yeah.
if the repairs are found quite fast. So we compute it in 10 seconds, 20 seconds. For most times what we need is for the most complex part of the repair computation is indeed the quantifier elimination. Z3 cannot handle quantifiers, and we have a lot of them in our formulas. And most time is afterwards needed for the admissibility check. So the most complex part is really the quantifier elimination, but for most time is used for the admissibility test afterwards.
Okay, so there is actually, I guess, a related question here for Amir Mohammed. Sorry, again, I'm gonna mess up all the names. Is checking admissibility always decidable in TarTar?
Yes, language equivalents for time-to-time and channel are not decidable, but the advantage that we have is that we use the untitled language, and this is indeed decidable, and we could reduce it to checking the equivalence of finite traces, which means that it's also in p-space, so it's quite nice.
Okay, that's nice indeed. Okay, thank you very much. I think that's, and let's move on to the next speaker. So we have Jacob van Geffen, I hope I'm reading correctly, from University of Washington, and he's going to talk about synthesizing JIT compilers for in-kernel DSLs.
Hello, I'm Jacob from the University of Washington. Today, I'll be talking about how to synthesize just-in-time compilers for in-kernel domain-specific languages. First, let's discuss in-kernel DSLs. For this, consider a user who wishes to modify the behavior of a kernel. This modification could be anything from packet filtering to profiling disk operations. She can express this behavioral change as an in-kernel DSL program. To modify the kernel, the user asks the kernel to run her program. The kernel may not want to run arbitrary user programs, so first, it will pass the program to a checker, which checks for properties like out-of-bounds memory accesses or unbounded execution. If the program fails the checker, the kernel returns to the user with an error. If it succeeds, the program is passed to an interpreter along with the starting state. The program is then run by the interpreter, and the kernel relays the output back to the user. For now, let's take a look at the DSL interpreter and the choices made at this point. For a language L, an interpreter is a function that takes a program in L and a starting state as input, then outputs a resulting state. In general, interpreters are relatively easy to write, but can be much slower than running native code. Performance is important here because in-kernel DSL code is run repeatedly in the kernel. These interpreters can also be susceptible to Spectre attacks. For these reasons, kernels often choose to run a program in L by using a JIT compiler. A JIT compiler takes a program in L and translates it to a target language T. The T program can then be run natively to produce the output state. While this JIT compilation process is often faster than the corresponding interpreter, they're more prone to correctness bugs. This is due to the fact that kernel developers must account for subtle semantic differences between the source and target languages. The question we hope to address with this work is, can developers write correct JIT compilers without the risk of bugs? With JITsynth, the answer is yes. JITsynth is our tool for synthesizing JIT compilers. Given interpreters for source language L and target language T, JITsynth outputs a verified JIT compiler from L to T. This allows developers to write JIT compilers with relatively little effort, all while avoiding bugs. Moreover, porting the language L to a new target only requires writing an interpreter for that new target, rather than writing a compiler. This talk has three main parts. First, I'll introduce the challenge faced by JITsynth by defining a search for mini-compilers. Next, I'll discuss the core of our solution, which is to organize the search as a complete metasketch. Finally, I'll discuss our evaluation, which shows that JITsynth can synthesize correct compilers for a variety of in-kernel DSLs. Let's get started with the challenge. Recall the model for an in-kernel DSL discussed previously. In this section, we'll pick a specific DSL for simplicity, eBPF. With eBPF, the user is an application such as the browser, and the programs sent to the kernel are packet filters. In reality, eBPF has been generalized to do more than just packet filtering, but that's not necessary for this talk. For now, think of an eBPF program as a program that accepts or rejects a given packet. As an example, an application may wish to accept all packets which begin with the byte 0x40. To do so, that application could submit the following eBPF program to the kernel. This program loads the first byte of the packet into register R2, then returns either an accepting value or an error value, depending on the contents. Note that for eBPF, the return value is stored in register R0. Now let's imagine the search space of compilers for eBPF, looking specifically at the following 4-instruction program. We want to compile this eBPF program to some target ISA T. For any real-world ISA, the size of our JIT will be on the order of 1,000 lines of code. However, modern synthesis techniques are only able to synthesize much smaller programs. Since synthesizing the entire JIT in one pass is infeasible, we instead synthesize a set of per-instruction mini-compilers. Each of these compilers handles a single type of instruction. For example, in this diagram, JIT MV32 is a mini-compiler which compiles the eBPF instruction move32 to an equivalent program in T. This allows us to break up our large search problem into many smaller searches. Once JITsynth generates mini compilers for each source instruction, it creates the overall compiler by stitching all mini compilers together with a sequence of conditionals. We have proven this construction correct using the lean interactive theorem prover. Now that we've introduced the problem JITsynth solves, I will briefly highlight the contributions of our work. The first is JITsynth, a tool for synthesizing verified JIT compilers for in-kernel DSLs given the semantics of the source and target languages. Second, we formalized the JIT synthesis problem as a search for per-instruction compilers between abstract register machines. Briefly, an abstract register machine is a language which operates over a state consisting of 3 parts: registers, memory, and a program counter. Further details on abstract register machines can be found in our paper. Third, we define a novel compiler metasketch, which takes advantage of domain knowledge to guide the synthesis search. In the next section, we'll take a look at our metasketch for JITsynth in detail. Finally, we evaluate JITsynth by using it to synthesize JIT compilers for 3 different source target pairs. So far, we've discussed the first 2 contributions. We'll now discuss the remaining contributions, starting with JITsynth's compiler metasketch. In this section, we'll briefly introduce general sketches, then show how to effectively explore our large search space using metasketches. Before we dive into metasketches, let's assume that we've already found a candidate compiler. How do we know if the candidate is correct? For example, suppose we've compiled this single add instruction. We can test the equivalence by starting with equivalent states, then checking to see if the resulting states are equivalent. In this case, they are. In reality, we want to be sure of equivalence for all starting states. We can do that with symbolic execution. Here, n represents an arbitrary value, or symbol. By starting with states that contain symbols, we can generate symbolic outputs that can then be compared. Specifically, JITsynth uses the symbolic execution engine provided by Rosette to do this. Given source and target interpreters in Rosette, JITsynth can test the correctness of a translation by symbolically executing the source and target program over equivalent symbolic states. The resulting states can then be compared with an SMT solver. Furthermore, we can even let compiled programs contain unknown values, which are considered holes. This compiled program with holes is called a sketch. Even though the sketch is incomplete, we can still symbolically execute it using Rosette. We can then ask an SMT solver to fill the holes in the sketch, requesting that the resulting state after the holes are filled is equivalent to the source output state. Now that we understand sketches, let's discuss the search space they represent. If we take the RISC-V ISA as our target language, we have about 100 instructions to choose from. We can also choose a distinct register for each of these slots. In addition, we can choose an arbitrary constant in the instruction. In the native search space, the choices for each instruction are also independent. This gives about 2 to the 60 choices for 2 instructions. To avoid exploring this search space naively, we instead can guide the search space based on key information about our domain. For example, if we're compiling an add instruction in the source, the target program will likely also use some arithmetic instruction. To guide the search space, we set up a hierarchy of sketches to try, defaulting to less restrictive sketches when one fails. This hierarchy of sketches is called a meta sketch. Let's look at how it works for the eBPF add instruction. First, we'll try a very limited sketch, which restricts the choices in many of the holes. If it succeeds, we get a completed program. Otherwise, we remove some restrictions on the sketch and try again. Similarly, on success, we get a completed program. If this sketch fails, we finally default to the naive sketch, which should cover the entire search space. We could succeed again here, but upon failure, we know that no 2-instruction target program will work. We then repeat the process for 3 instruction programs. Since the search through naive sketches may actually be slower than longer but restricted sketches, we run the search for differing length compilers in separate threads. We've constructed the search process to cover the space of all programs of a given length, so we know that our search is complete up to this length. Let's now discuss our 2 main metasketch optimizations, the first of which is the read-write sketch. This sketch takes advantage of read and write information. Specifically, JITsynth restricts sketches to only include instructions that read from and write to the same parts of the state. Recall that a state is made up of registers, memory, and a program counter. Here, the eBPF add instruction reads R, a register, and writes a new value to R. Similarly, the add and subtract RISC-V instructions both read and write register values. The jump instruction JEQ reads register values, but it also reads and writes the program counter. The load instruction reads memory, then writes to registers. With this information, JITsynth will try a sketch that rules out both the jump and load instructions, since their read and write information differ from eBPF add. This optimization may rule out valid target programs, but that is fine since we default to a less restrictive sketch in that case. We call this information read-write sets, since each instruction can read from and write to a certain set of state attributes. The 3 pieces of state, registers, memory, and the program counter, are written here as reg, mem, and pc for simplicity. JITsynth computes the read and write sets for each instruction by using symbolic execution. To determine whether or not a state attribute is in the write set for an instruction, JITsynth executes the instruction over an arbitrary symbolic state and determines if the instruction could change the state value. If so, then the state attribute is part of the write set. In this case, m may be non-zero, so reg is in the write set. Computing the read set is similar, but requires 2 executions. To determine if a state attribute is in the read set, JITsynth executes the instruction under symbolic states that are equivalent in all other state attributes. If the resulting states could differ, then the state attribute is part of the read set. In this example, since A and B may differ, reg is part of the read set. Our second metasketch optimization is the preload sketch. For this, let's again consider the eBPF add instruction. On the right, I've written a sketch that we might want for a RISC-V compiled program. There's a problem, however. Specifically, we cannot simulate add with this sketch because the RISC-V instruction does not have enough space for the constant m. In general, this problem occurs whenever the target language lacks big enough constants. To get around this, JITsynth searches for a target program that first loads the large constant into a temporary register, then uses that value. For add, it looks something like this. The first instruction in the sketch loads m into a temporary register t0. Then the second instruction performs some operation using t0. The actual operation is still undecided, but the search space is much smaller. This begs a question. How can JITsynth find these preload commands? The answer is by using read-write sketches. Specifically, JITsynth can search for a preload program that only uses instructions that read and write to registers. Using Rosette, JITsynth is able to find a program that moves the source constant into a particular temporary register, in this case T0. With our Metasketch optimizations explained, I'll conclude the talk with JITsynth's evaluation. Our evaluation aims to answer two main questions. Can JITsynth synthesize correct and performant compilers? And how effective are JITsynth's Metasketch optimizations? We synthesized 3 compilers with JITsynth to answer these questions. Let's take a look at the first question. Our first synthesized compiler takes eBPF to RISC-V. To measure performance, we compiled several real-world eBPF filters, ran those filters with a predefined packet, and took the average runtime of all filters. When compared to code from a handwritten Linux JIT compiler, the JITsynth compiled code ran about 1.8 times slower on a RISC-V processor. This is due to the fact that handwritten compilers can make nuanced optimizations based on the value of source instruction parameters. However, the compiler JITsynth generates avoids bugs found in a Linux handwritten compiler. Specifically, the Linux handwritten compiler incorrectly compiled 32-bit arithmetic operations due to semantic differences between eBPF and RISC-V. In addition, when compared to the Linux eBPF interpreter, we get an average speedup of about 5 times. Thus, JITsynth provides a helpful step towards generating both correct and performant compilers. Next, I'll address our second evaluation question, which asks if our Metasketch optimizations benefit JITsynth. To determine this, we ran JITsynth over 3 source target pairs, both with and without optimizations. With full optimizations, JITsynth was able to synthesize all compilers. However, without optimizations, JITsynth timed out on 2 of the 3 pairs and had significant slowdowns on the 3rd. This leads us to believe that the Metasketch optimizations JITsynth uses are in fact necessary. With this evaluation, we can conclude that JITsynth is able to synthesize correct and performant compilers, and that the Metasketch optimizations we discussed help to do so. To summarize, today I presented JITsynth, a tool for synthesizing verified JIT compilers for in-kernel DSLs. JITsynth solves the search problem for mini-compilers between abstract register machines. In order to solve this problem, JITsynth uses a novel compiler Metasketch to direct the search. Using JITsynth, we have synthesized 3 compilers for real-world DSLs. You can find the JITsynth artifact at the GitHub link shown here. Thank you.
Hello.
Hello. Hi. Really nice talk.
Hey.
Thank you. Yeah, I particularly like how you guys go around the scalability issues by, you know, just synthesizing these mini compilers and weaving them together is very nice. So thank you.
Thanks.
And I have some questions. So the first one from Tanimochi. So thank you for your nice talk. Source DSL is fixed to eBPF in your talk. Can a source DSL beat some ISA? If so, can you support when source DSL is context sensitive?
Yeah, so the DSL isn't fixed to eBPF. You can also make it an ISA. Of course, if the translation gets to be too big, meaning like that if each of the mini compilers is going to become really large, it will have a much tougher time scaling. But as long as you can write an interpreter for both of them, you can definitely do it. As for the context sensitivity, we ignored function calls for this. So, but I don't think that extending it to be context sensitive would be too difficult. Basically, if you can write an interpreter for each of the instructions, like in the DSL, then you can do it.
Okay. Thank you. There is another question from Sri. How does this approach compare with the more traditional approach of overcoming the inefficiency of interpreters by partially evaluating the interpreter with known or fixed inputs?
Gotcha. So yeah, I'm not entirely sure how to answer this. So, yeah, I don't know. Sri, can you maybe explain a little bit more? So, so what we're doing is, I guess, maybe like a little bit more general from that. So we're kind of considering that, you know, a source program can have pretty much any input. So that's how we're using symbolic execution for that. Maybe I can better answer this offline. I'm sorry.
I have a question. You know, if maybe we can move on to that, and you can take this offline. You have this slide where you discuss the search space for sketches, and you know, I noticed that constants are like a serious source for like blow up there.
Mm-hmm.
So I'm wondering if you have any strategy for dealing with constants in particular. Like, I don't know, the simplest one that I can think of is just prioritizing sketches that don't use constants or something like this. Do you do anything special there?
So we don't do anything special. We definitely thought about it, and it ended up being, I guess, not super necessary. We were like relatively happy with the results, and there were some cases, you know, where the JIT took quite a while to synthesize the compiler. So optimizations like this could definitely help in that case, but we didn't do that for this work. So that's a good suggestion, though. Thank you.
Okay, thank you. Yeah, I think the time is up. So thank you very much. And let's move on to the next talk. We are going to have Yanju Chen from University of California, Santa Barbara, talking about program synthesis using deduction-guided reinforcement learning.
Hello, everyone. My name is Yanju Chen. I'm from UCSB. Today, I'm going to present our work, Program Synthesis Using Deduction-Guided Reinforcement Learning. This is joint work with Chenlong Wang, Osbert Bastany, Isha Dilek, and Yu Feng. As we know, program synthesis is getting more and more attention nowadays. It also has many exciting application scenarios. Given specifications phi, the goal of program synthesis is to find a program P that satisfies all specifications phi. For those applications such as table transformation, data visualization, string transformation, and high-performance computing, there are many related good research works and tools. And as we also know, one of the biggest challenges of program synthesis is about its huge search space. There are different approaches that try to address this problem. For example, the deductive reasoning approaches try to cut the search space by logical deduction. And the statistical reasoning approaches try to promote the promising candidates programs by data-driven inferences. Even though we see many tools that either use deductive or statistical reasoning approaches. Also, there are many of them trying to combine the benefits of both. There is still a fundamental disconnection between the two approaches. Because the feedback generated by deduction usually, in most cases, cannot be directly used to update the statistical model in a seamless way. As we know, deduction can provide rich information because it not only returns yes or no answers when given specifications and a program, but also, for example, can return programs that are equivalently incorrect regarding the provided program. So such rich information feedback is usually provided in deductive synthesis tools, while in these tools, the statistical components are usually fixed. So you may wonder whether we can bridge the statistical and deductive approaches in program synthesis in a seamless way. Well, the answer is yes. We propose Concord, a framework that utilizes fine-grained feedbacks from deductive reasoning to update statistical reasoning on the fly. So what exactly is Concord? Here's an overview picture of Concord. There are three components in Concord. The take action component will take into account of an initial policy, which will be used to propose a partial program or a program P. And this program will be fed into the deduce module. The deduce module will tell whether the program satisfies the user intent or not, and tell more details about the reason and provide further feedbacks. And its update policy will take into account of all those feedback provided by the deduce module, and then try to update the policy on the fly. And this newly updated policy, which takes into account of all the suggestions from the deduce module and all the suggestions from the training data, will be reduced again by the take action to provide better suggestion and proposal of the program. So in order to move on to the details, let's first start from a learning example. Suppose that a user wants to study the behavior of koala, and she has two lists of tracking data collecting from the koala itself, and then she wants to design an algorithm that tries to aggregate these two lists into one. So here's the algorithm that she designed. First of all, she wants to reverse the first list and then do a cumulative sum of the second list. And eventually, she will do a subtractions between these two lists, and then she'll eventually get the desired aggregated list she wants. Since she's not an expert in programming, she will have to refer to program synthesis for help. Notice that this is a typical list processing problem. So here we provide a sample DSL for doing list processing. This DSL contains several commonly used list processing components. For example, take and drop will respectively take and drop the first n elements, which will result in the change of the size of the list. And sort and reverse will change the ordering of the elements in the list. Add and sub will modify the the values of the list elements. Finally, sum up to will change the list to its accumulated summary form, in the sense that the ith elements of the output after applying sum up to will be the sum of the first I elements of the input. So the solution programming looks like this. So the task of the synthesizer is to find out the solution program with its given input-output example as indicated here. So let's see how do the two approaches work here very quickly. So for deductive approaches, this picture shows you a variant of the CGS loop. There are basically two components in the CGS loop, namely a decider and a deducer. For this loop, the input will be the specification fee, a DSL, and knowledge base. Notice that the knowledge base here can be the simple data structure that stores all the rejected programs, so that the decider will not have to enumerate it again. So every time when the decider proposes a new program P here, this P will be fed to the deduce module. And the deduce module will tell the feasibility of this program. Here we say a program is feasible given specifications if it satisfies the user intent on a logical level. So as we can see, this program is infeasible. Why? Because as we noticed that the inputs have the same length of the list as the output. But this take component here is actually changing the size of the list. So this will result in a violation of the user intent. Therefore, this program is infeasible. So besides returning a feasibility flag, the deduce module can provide further information about whether there are any other programs that are equivalently infeasible. And this information will be provided to the decider, so that next time when the decider wants to propose some new program, it will avoid all those rejected programs until it reaches the correct solution. There are pros and cons. On the one hand, the deduction is pretty rich and accurate, and the pruning of the search base is pretty efficient. On the other hand, incorporating such deductive feedback into existing statistical model is pretty difficult, especially when the decider itself is a statistical model. So how about this statistical model? We can see the statistical model will take into account of the specification fee, DSL, and an initial policy, pi 0. This initial policy can also be a pre-trained model. So the infer module here will try to utilize this initial policy to propose the best program that it knows, which corresponds to this one, and the program will be checked by the checker to see whether it satisfies the input-output example or not. And the checker eventually will return a yes or no answer. If it's no, and if we are in an online learning setting, and this yes or no answer can be used to update the policy itself. If no, then we'll move on to the next candidate. So until we move to the correct solution here. So there are also pros and cons here. On the one hand, the candidate list is derived from a data-driven model, which can better reflect the user intent, and then we can update the policy in a seamless way. On the other hand, the feedback from the checker is relatively less informative than that from the deduction. So back to the Concord overview. We can see, as you may have already noticed, Concord shares some similarities between both statistical methods and deductive methods. From the perspective of statistical methods, it also takes into account of an initial policy. It also has a take action module that consider the policy to propose programs. And it also has an update policy components that update the policy itself so that the take action can consider a new policy after every loop. And from the perspective of deductive approaches, it also has a deduce module that can tell in details about the feasibility of the proposed program and provide more information about it. So here the key part that makes Concord different is that the feedback from the deductive reasoning part can be seamlessly incorporated to update the statistical reasoning part. So to understand the core part, I will first do a very brief introduction about the formalization. Think of a finite state machine where every state represents a program that is either partial or complete. We start at the initial state, which corresponds to a whole that represents all possible programs, and transit to another state by picking a production rule, which with certain probability to expand the current program to make it more complete. For example, here we pick L, and then we pick sum up 2 as a production rule with the probability of 0.3, then we can make this program more complete by expanding this node. So by doing this iteratively, we gradually complete a program by making a sequence of decisions in order to reach the final state. We call this the Markov decision process. Specifically, states will be assigned rewards, which measures how the corresponding program comply with user intent. For example, this program is actually feasible, so we can give a positive reward here. So program synthesis can be formalized as an MDP in the above-mentioned way, with the final target being to maximize the rewards here. So notice that the bigger the rewards, the better the program can satisfy the user intent, so the higher chance that you can find the correct solution. So after knowing all this, let's see how Concord works on this running example. So as you can see, in every loop here, every time detection will propose a new program, and this new program will be checked by the deducer here. So this part is pretty similar to the deductive approach. So according to our previous analysis, deduce will return invisible because the first program actually violates the user intent. So here in Concord, besides returning invisible, deduce will actually return the sampled invisible programs, which indicates what are the other programs that are guaranteed to be invisible. So this actual list will be provided as extra training data to the update policy module. So the update policy module will utilize this extra training data to update the policy. And the next time when this take action wants to propose a new program, it will have a new internal updated candidate list. As you can see here, there are some programs that are getting downgraded by this policy, and then some of them are actually getting promoted. So the actual candidate list may look like this. So luckily, by considering all the suggestions from the feedback of the deduction, we can try to promote those programs that we want according to the user intent, and at the same time reject those programs that we don't want. So luckily, if we hit the correct solution in the very first place, it will move on smoothly and eventually will reach the correct solution. So what are the differences here? So there are two differences. First, the feedback from deduction can flow seamlessly to the policy updates. And second, the Concord framework can not only prune the search base, but also promote the good candidates. So what's the difference here? You may notice that there's a secret in this deduce and update policy modules. So let's zoom in a bit to see the details about it. So here you can see this is a zoomed in deduce module. It takes into input a program and then in the output a sample invisible program list. So what's inside it? Actually, it has two subcomponents here, a deduction engine and a sampler. The deduction engine is pretty similar to the deduction procedure in deductive approaches, in the sense that it will return visible or invisible. And when it returns invisible, it will also return a list of logical constraints indicating what are the other programs that are equivalently invisible as the input program here. So notice that we cannot directly utilize these logical constraints, as we mentioned here, into updating the statistical model. So here we need to introduce some translator that translate these logical constraints into some compatible data formats with the statistical model. So here, this sampler is actually doing the sampling of all those invisible programs based on the pattern indicated by these logical constraints. And eventually, we'll have these sampled invisible programs as an output, which can be further provided to the learning of the statistical model. So outside here, we can see this list will directly flow to the update policy component, and the update policy component will utilize that to update the policy pi. So there's a problem, because previously, when we do the update policy, all those programs are translated, or all those programs are sampled from using the original policy pi here. But since we're introducing a new sampler here, we're actually introducing a different policy, a different distribution other than the original policy. So we call this off-policy sampling. So in order to incorporate these off-policy samplings into the original policy updates, we need to introduce a new factor called importance weighting to make this work. How do we do that? So here is the formula that we use to compute the gradient of the rewards. So notice P corresponds to the partial program that we have, and this D of pi theta is actually the program distribution of the original policy, and this L is actually the weighted future rewards. So this first line is actually computing the gradients if we are actually sampling from using the original policy. But since now we are changing the policy to some other different policy here, so this D tilde is actually the program distribution of the sampler. So in order to incorporate that, we need to add a new factor called importance weighting here. So semantically speaking, this importance weighting is measuring or estimating the probability of sampling those programs from this invisible program list from the actual policy pi that we're using. So it's estimating some probabilities here. So for more details about the theorem and proof, you can always refer to our paper. So evaluations. So here we are interested in two research questions. The first one is, how does Concord compare against the existing synthesis tool? And the second is, how effective is the out-policy sampling? So we use Neo's deduction engine here, and then we use GRU as the policy, because it's the popular neural network for modeling sequential decision. And for benchmarks, we use the decoder benchmarks in Neo. It contains 100 challenge list processing problems. We'll compare these two against Neo and decoder, where Neo is the state-of-the-art synthesizer by using the deductive approaches, and decoder is an approach that uses pure statistical reasoning. So this is the result figure. X-axis corresponds to the number of benchmarks solved. Y-axis corresponds to the cumulated time spent on solving all those benchmarks. As you can see, the lower the figure, the better the performance. So actually, Concord is solving more benchmarks than the other two tools with an average time of 36 seconds, which is much less than the other two tools. So I believe this answers the first research question in a positive way. For the second research question, we devised a variant of Concord with all the off-policy sampling learning removed. So as you can see, this new variant is solving a fewer number of benchmarks with a lower speed over Neo. So I believe this also answers the second question in a positive way. So the takeaway message is, Concord can tightly couple statistical and deductive reasoning based on reinforcement learning. And the off-policy reinforcement learning technique is actually effective. So for more details about the evaluations and its settings, as well as the ablation study, you can refer to our paper. So with all this, I'm happy to take questions. Thank you.
Thank you very much for the talk. A very nice way of integrating deductive power into reinforcement learning. And we already have some questions. So the first one is from Cesare Tinelli. Thanks for your nice talk. How does the deductive engine determine whether the candidate program is feasible or not?
Thank you. Yeah, that's actually, can you hear me? Oh, yeah. So that's a good question. So in our framework, the deductive engine can be, it's pretty flexible. So particularly for the deduction engine that we use to run our experiment, we will use the Neos deduction engine in the sense that it's a typical deduction engine where you run deduction on the, like, for example, you encode the user intent as logical formulas, and then you encode the partial program as logical formulas, and the deduction engine will check whether those two formulas, whether this is satisfiable or not. So by doing this, we can tell whether a program is feasible or not. But this is just one example of the deduction engine. So our framework can actually accept different deduction engines given like different requirements or needs. Yeah. Good question.
Okay, thank you. The next question is from Amir Mohammad Nazawi. And the question is, what is your reward function for Markov decision process? Can you explain more about it?
Oh, I see. So actually in our experiment, we have, so you can actually decide your reward function in a more adaptive way. But in the experiment, our reward function is decided in this way. If the program is feasible, we'll assign +1. If the program is infeasible, we'll assign a -1 or 0, like this. So this is a simple reward function, but of course you can customize a more like sophisticated reward function in your own experiment. Yeah.
Thank you. Another question from Ivan Gavran. Thanks for the talk. Can you say something more about how the policy update works? Which programs get updated and how?
Oh,
sorry, upvoted and how?
Okay, so I'm not sure I entirely understand the question. So I suppose that you're asking about the policy update part or the policy like a sampling part. So I'll answer both. So for the policy sampling part, every time, because we formalize the MDP, formalize the program synthesis MDP, so every time we will try to complete the program a little bit step by step by picking up all those production rules. So the policy will pick production rules and complete the program bit by bit. So for the sampling part, because the deduction engine will return some logical constraints, we need a sampler to try to translate those logical constraints into a different data, into a list of data. So this data can be provided to be the learning data of the policy. So yeah, so I hope that answered the question.
Okay, thank you. And one last question, it's from Elizabeth Polgreen. So she says, interesting work. If I understood correctly, you implement the technique for list manipulation programs. Do you have any intuition on how well this approach would work for other types of synthesis problems? For instance, for bit vector arithmetic or LIA in the SIGAS competition. Have you tried this? Do you have plans to try this?
Yes, definitely. That is a very good question. Yes, I was going to mention that. Yeah, we are planning on doing that, and actually we're actively working on that. So but there are some adaptation works to do because, for example, you need to have a statistical model ready to like give you the ranking of those programs. So you need to probably so some domains you need a sampler, a program sampler, something like this. And another part is the sampler inside the deduction engine. You need to have a translator that can translate what is returned by the deduction engine into the some compatible format that is acceptable by the statistical model. So we're actively doing it, definitely, but it will need some adaptation work. Yeah.
Okay, great. Yeah. Thank you very much. If there are more questions, I think they can be taken on Slack. But thank you very much for a great talk. And
thank you.
Yes. And now we can go to Paul Krogmeyer from University of Illinois at Urbana-Champaign, who's going to talk about decidable synthesis of programs with uninterpreted functions.
Hello, everyone. This is Paul speaking. Today I'll be talking about a decidable program synthesis problem for programs with uninterpreted functions. This is work with Umang Mathur, Adit Imarali, Madhu Parthasarathi, and Mahesh Viswanathan at the University of Illinois Urbana-Champaign. Are there decision procedures for synthesizing programs with loops that work over infinite domains? This is the question we address in this work. And the flavor of program synthesis we're looking at here is much like Sketch or Cygus. So given a partial program with these question mark holes, we're asking a synthesizer to give us back a program where the holes have been filled so that some correctness specification is true. In our case, the correctness relies on assertions peppered throughout the input. But there's another amendment to make here. In our work, symbols like greater than or equal to here, addition, multiplication, these are all uninterpreted. So now I've replaced those relations with capital letters R and Q, and the functions with lowercase letters F and G. And correctness of a program in this setting is with respect to all interpretations of the symbols. So as an example interpretation, you pick a domain. Here's one of size 2. You pick an interpretation for the constants. In this case, there's 0 and 1. And you pick interpretations for the other symbols, the relations, the functions. And a program has to be correct, meaning its assertions should be true for any of this kind of choice of interpretation. So it's in this sense that our programs work over infinite domains. It's okay if this idea is a little bit murky. For the talk, we won't really need to understand the semantics in any detail. The input to our problem is much like a sketch. It's a partial program with holes, but we're going to want to think instead of the input being a context-free grammar, like the one on the right here. Then the output is a program from the grammar such that all of the assertions are true. Of course, we're working in an uninterpreted semantics, as I said, but we can forget the details of that and think abstractly of assertions being true where the semantics is sort of a parameter of what I'm talking about. The problem's called grammar restricted synthesis of uninterpreted programs. Given a grammar for uninterpreted programs, synthesize a correct program from the grammar. The problem's decidable for a subclass called coherent uninterpreted programs. This is a fairly technical restriction, which I won't talk about here, but you're welcome to see the paper for some examples. The programs we synthesize are infinite domain programs with loops and recursion. I also won't talk about recursion, but please see the paper if you're interested. And including a grammar in the definition makes the problem hard. There are lots of trivial uninterpreted programs which are correct. For example, those that don't have assertions. So the grammar crucially makes the problem hard. Let's think about the simple programming language here, which I'll just call simple. There are assignments from variables, assignments from functions applied to variables, assumptions, assertions, sequencing of statements, if then else, and while loops. And the conditions are Boolean expressions over relation symbols and equality. I'm going to talk now about building up a program synthesis search space by defining various automata. Here's a roadmap for that. On the right, you see 3 different automaton models, and on the left, the objects that they work over. We'll start with executions. Executions are finite words over a rather complicated finite alphabet sigma of statements, assumptions, and assertions. W is an example here. We'll say an execution is correct if all its assertions are true. And a program is correct if all its executions are correct. For any given simple program, the set of executions it generates is a regular set. Take as an example the if then else program on the left here. It generates 2 executions. The one on the top corresponds to taking the then branch, so assuming that the guard is true, then branch, and then the assertion after the if then else. And on the bottom, the execution for going into the else branch, you assume the guard is false, else branch, and then the assertion. Take another example, the while program on the left generates an infinite set of executions, one for never entering the loop, so assuming the guard is false, and then hitting the assertion after the loop, going through the loop body a single time, assuming the guard is true, body of the loop, assuming the guard is false, and the assertion. And we can write the full set of executions as a regular expression using clean E star. So the point is, the set of executions for a given simple program is accepted by a finite word automaton. We would be happy, though, to have not just an automaton for executions of a given simple program, but correct executions. Now, these won't be regular in general. They won't even be decidable in general if you have assertions that talk about multiplication over integers, for example. But I want us to suppose that correct executions were regular for simple programs. I'll call such an automaton a hypothetical automaton. I'll call it A. And now I want to ask, what could we do with A if it existed? Well, we could do emptiness checking. This would essentially give us a synthesizer for correct executions. But as we just saw, programs generate many executions. So we'd like to take a step toward program synthesis by looking at objects which represent many executions. And that object is an execution tree on the left. Its corresponding automaton model is a top-down tree automaton. So if you haven't seen tree automata, here's a little bit of intuition. These are a straightforward generalization of word automata, at least in our case. They work on labeled trees like the one on the left here. And a top-down tree automaton will start at the root of its input tree. It'll read the label A here. It's starting in some state. And it'll choose two states to go to in the children subtrees. So then a run for a top-down tree automaton is also a tree, where the nodes of the tree are labeled by states of the automaton. We can contrast this with the transition function for a word automaton, like A. Here I'm writing a possible transition function for a tree automaton, delta tree. And I've written it so that it simulates A on each of the branches of an input tree. So if we're taking A to be this hypothetical automaton which accepts correct executions, then this delta tree transition function would define a tree automaton that accepts execution trees whose branches are correct executions. This is a key idea that we'll use in our solution for program synthesis, simulating a word automaton on the branches of a tree. Concretely, we then go back to the if-then-else program on the left and its execution tree on the right. This is basically just unfolding the program into the possible paths that it can take. And remember, I said we want to imagine simulating the word automaton A on the branches of the execution tree. So each of these will have read either the guard being true or being false, and they're simulating the statements that they find in either the then branch here or the else branch over here. Then they each hit the same assertion, which follows the if then else in the program. And the execution tree is accepted if all its branches are correct executions. So this is fine, but it's a problem if we go back to the program synthesis view based on sketches. Here I've replaced the if then else's assertion at the end with a hole, which can either go to code 1 or code 2. And then I've taken the execution tree, and in the left branch I put code 1, and in the right branch code 2. And now there's a problem for tree automata here. They can check that the branches are correct. There's no way for them to ensure that the hole is a single hole in the specification. There's no way for them to ensure that it's filled uniformly with code. There's a sense in which the control of the automaton on each branch can't communicate. So the solution is to change the input tree. And that solution is program trees. These are like abstract syntax trees. They're finite trees that represent infinitely many executions. And what we'll want to do is define an automaton whose language is program trees that only generate correct executions. So the corresponding automaton model we'll use for these is two-way tree automata. Taking that idea in the context of the program with whole, the if then else on the left, we get a program tree with a whole on the right. And this has solved the uniformity problem. There's a single hole in the spec and a single hole in the tree representation that we would be reading. That's good, but there's another problem. Imagine trying to define a top-down tree automaton, which checks that the program tree it's reading only generates correct executions. So you could read the if and read the right subtree, and whatever's here in the hole, whatever concrete code is here, to decide if it's correct requires knowing what happens in the left subtree. This is just by virtue of the semantics of sequencing one statement after the other. So a solution to this is to use two-way tree automata, which can naturally model control flow. And what we have here is a picture of how we use two-way tree automata to define a set of correct program trees. So program trees that only generate correct executions. And we can use our word automaton for correct executions, and we can simulate it up and down an input program tree. This is what two-way automata allow us to do. So I'll just show you a picture of that happening. Here's the execution automaton A. It's reading the guard of the while loop. It's going to spin off two copies of itself, one corresponding to the guard being true and entering the body of the loop, and the other to it being false and exiting. Let's pay attention to the one going into the loop. Here now it's reading the guard of the if then else. It'll spin off two more copies, one corresponding to the guard being true and the other for it being false. Each of these copies will read its leaf statement and head back up the tree. And now both of these are reading the guard of the loop again, and each will spin off another copy corresponding to the guard being true and being false. So this is the high-level picture of how a two-way tree automaton can be defined. The final piece of our puzzle is to recognize that the grammars and sketches that we care about correspond not just to context-free grammars, but regular tree grammars. So the point of that for us is that for an input grammar G, it will correspond to a regular set of trees, which will have a small top-down tree automaton, AG, that accepts that set. I've explained that we can define two-way tree automata to accept program trees that only generate correct executions, and that we can define a top-down grammar automaton which accepts program trees that follow an input grammar. And now I'll answer the question posed at the beginning of whether or not this correct execution automaton A actually exists for a programming language. Our results for uninterpreted programs use the ideas you've just seen, along with a key observation from earlier work, which saw that there is a correct execution automaton for a subclass of uninterpreted programs. This class was called coherent uninterpreted programs, and it contains many natural one-pass algorithms. For example, searching in a list or a tree for a key. Here's a picture of our decision procedure. We begin with the correct execution automaton AX. Its size is exponential in the number of variables appearing in the input grammar. That's n here. And then we take that and we build the two-way automaton as I described. We then convert that to a top-down automaton. This incurs an exponential blow-up in the number of states. And we can do that by framing the membership problem of the two-way automaton as a finite reachability game. And we do this conversion from two-way to top-down because ultimately we would like to take the product automaton with the grammar automaton, which is already top-down. So after the conversion, we can do that, take the product, and we get a final automaton ACC of size doubly exponential in the number of program variables in the grammar and linear in the size of the grammar. So the language of ACC is the intersection of these two languages. So that's the set of correct program trees that follow the input grammar. So we've reduced program synthesis to checking whether or not the language of this final automaton is empty or not. And if it's not empty, we can search and pull out witness program trees. Our main theorem then says that grammar-restricted program synthesis for uninterpreted coherent programs is decidable and 2x time complete. As a corollary, we also get that Boolean program synthesis is 2x time complete. There's more in the paper, including lower bounds for these results, recursion, and related synthesis problem for transition systems. To summarize, I showed you we can combine execution automata with tree automata, and I showed you an instantiation of those ideas for uninterpreted coherent programs. And this gave us a decidability result for infinite domain program synthesis. In the future, it would be nice to look at finding practical program synthesis uses of these that work on the basis of these ideas. The final automaton we get in the decision procedure is too big to implement explicitly, but there could be some way to cut some corners and make use of the ideas anyhow. I think that our solution instantiates a general idea that we can study program synthesis under the lens of tree regularity for grammar and control flow, and word regularity for execution semantics. Thanks a lot for listening, and looking forward to answering your questions.
Hi, thanks a lot for the talk. Before we go to the question, because there are actually quite a few, I have to say that I was really, pleasantly surprised by your result, because I did not think that the class of programs for which syntax guided synthesis basically is decidable is that rich. So thank you. And now I'm just going to read some questions. So the first one is from Shuvendulahi. How does the decidability of synthesis hold for simple relaxations of coherent uninterpreted program condition, such as program with a partially interpreted functions, for instance, for all x, prev of next of x equals x is a precondition for circular linked list reversal or commutativity of addition?
So the coherence condition is it's pretty tight. So it actually consists of two things, which I could maybe talk about on Slack if you want. But if you drop either one of them, you kind of lose what you need to get at least decidable verification of correctness of executions. But there's also some work that's looked at adding some axioms and seeing if it still is decidable. But I'm not sure for the one that you give as an example if it would be. Yeah.
Okay, then maybe you can discuss more on Slack, and we can go to a question by Cesare Tinelli. I do not see how the vocabulary for the regular language of executions is finite. What are the elements of the vocabulary?
So there's a finite number of variables, and there are a finite number of function symbols and relation symbols. And the letters are statements, assignment statements, assertions, assumptions, and the conditions we can take Boolean expressions and kind of model them. And what we end up with is assumptions and assertions over equalities and disequalities between variables after some modeling tricks. I'm not sure if that helps.
Okay, again, I guess you can settle that
sure. Yeah.
on Slack. The next one from Shoal Almagor. Thanks for the talk. When a program is not realizable, is there a notion of counter strategy for the environment? What kind of interpretation is that counter strategy over?
I think I'm not sure what you mean.
If you can just say what I mean. So in the synthesis of the game, if you have the environment and the system that interact, if the system is, if the specification is not realizable, does the environment have some kind of counter winning strategies? And
so, right, okay, the lower bound, so that the program synthesis problem is 2x time hard. You can kind of look at the proof for that as a game. So there is a notion of strategy there, but I'm not sure about thinking about it as an environment. But there is a notion of strategy, and it's kind of related to, so I mentioned that we also looked at transition system synthesis, and the program synthesis problem. There's a notion of like information hiding that you get that kind of comes into the game picture when you try to prove the lower bound, that you don't get for transition systems. And with programs, you can sort of hide information. In the case of an if then else, it's a question of whether after an if then else, do you know how the guard evaluated or not? So there, I think I'm losing your question here, but the point is there is a notion of strategy, but I'm not sure it's really quite what you're thinking of.
okay, thanks.
Okay, the next one from Irat Kalimov. Is it possible to extend to liveness properties? You use only assertions, which are safety.
I'm not sure. I think that's all I can say. I'll think about it. Maybe we can talk on Slack.
Okay, and then I think I'll just take one last question because
Sure.
we already had quite a few. So it's from Amir Mohammad Nazari. Uninterpreted functions sometimes are called holes of the program. Imagine the number of holes of the program is large. How efficiently your approach fills the holes? Can we use the approach for large programs?
Yeah, I don't think the number of holes plays a big role here. So I mean, yeah, I mean, this will appear in what the grammar, the input grammar will have these some non-terminals, which are basically describing how the holes can be filled. And I don't think that'll be a big issue for the complexity. It's more in the number of variables. Yeah.
Okay, thank you. I guess the good part about having all these questions on Slack is that you can actually continue the conversation there and maybe clarify whatever is not fully clear at this point. But thank you very much for the talk. It was very nice.
Thank you.
Thank all the participants and everyone that attended this session. And please join the breakout session now. And yeah, see you. Bye-bye.
Bye-bye, thanks.
Thank you.
Thank you. Thank you.